So this material is bronze, and this is aluminum. Okay. All right. So they give you information about bronze and aluminum. So let me list that for you. For bronze, I'll just call, what did I call bronze? I called it B. Okay. So I'm going to call bronze B. So bronze and aluminum is AL. So the area, they give you the area of this cross section over here for the bronze. That's 2.4 inches squared. This is given. Okay, they give you the Young's modulus, which is 15 times 10 to the 6 psi. They give you alpha, which is equal to 12 times 10 to the negative 6. This number should always be really small. It's 1 over degree F. And for aluminum, they give you the same things. They give you the cross-sectional area, which is 2.8 inches squared. They give you the Young's modulus, which is 10.6 times 10 to the 6 psi. And they give you alpha, which is equal to 12.9 times 10 to the negative 6, 1 over degree F. Okay, so this is the information they give you, and they say, knowing that there's a gap of 0.02 inches exists between the bronze and this wall over here, they want to know, they give you the initial temperature. So they say, as this is the initial temperature of this whole setting, Ti is equal to 75 degrees F. And they're asking, what is the final temperature when the normal stress in the aluminum bar is minus 11 ksi? So they also give you this piece of information. The normal stress of the aluminum is equal to minus 11 ksi. Okay, so they give you a lot of information, right? So what you have to understand what's going on in this problem. Do you guys understand what's going on in this problem? They're allowing this material to heat up. So when it heats up, what happens to metal when it heats up? It expands, right? So it expands, okay? And they give you a gap. So what's happening in this problem is this is going to continue to heat up until it hits the wall, right? Both materials are going to expand, and eventually this bronze is going to hit the wall. What happens after it continues expanding? After it hits the wall, it can't expand anymore, right? But it's going to get compressed, right? That's why they give you the normal stress in the aluminum. Because right now, as it is, without the temperature increase, there's no stress here and there's no stress here. Why? Because there's no force. So there's no stress right now when the temperature is 75 degrees F. But when it continues to expand until the final temperature, which you're asking for, they're saying at that temperature that you're looking for, aluminum is 11 ksi. Okay?
Wouldn't it bend downward though if it's like that? And
Yeah, it would, because this has a weight and this has a weight. But ignore that. They don't give you the weights. They don't give you the density of each one. You know, because if you know the density and you know the volume, you can get the mass multiplied by gravity. You can get the weight of each one. Yeah, but that's another problem. You could get something like that in chapter 9, but not in this chapter. Okay, so this is all the information. So everyone's comfortable understanding what's going on in the problem? Because that's the first thing. When you see a problem, you're like, what the hell do I do? I have all this garbage. Like, what do I do? So you have to get into like the mindset of figuring that out. So that's how I do well on tests. That's what I do. I'm like, what do I have to do? You know, so we'll figure that out before the exam. That's what I'm trying to say. Okay. All right, so you have all this information. What you do know is that, what do you know after this gap closes from statics? What do you know? Once this closes, what's the force in this one and what's the force in this one?
They're going to be the same.
They're the same. Why? That's right. That's good. See, does anyone else know that? Or he was the only one who knows? Okay. Yeah, they're the same, okay? You guys just did the homework. You should know this. But that's important to know, right? Because these aren't loaded, right? This isn't loaded and this isn't loaded. So when this closes, the force on this one has to be equal to this one. If you sum the forces, this force has to equal this force. There's no other, they don't give you like a force here or anything, so that's good. That's what you have to know. That's what I was looking for, okay? So go study with that kid. Okay, so So these two forces are the same, right? So what do you know from mechanics? So from statics, we know the force in the bronze is equal to the force in the aluminum. Okay? So we'll just call that P. Doesn't matter. But we don't know what that is yet. But we can find it, right? Because we have the stress in the aluminum. So since we have the stress in the aluminum, we know the cross-sectional area of the aluminum, we can find that force P. Right? So let's just find that right away to get rid of that. That's something we could find right off the bat. So we have sigma AL is equal to minus 11 KSI, right? So we know sigma AL is equal to the force in the aluminum, which is equal to P. And it's minus, right? Because it's being compressed. So it's minus P over AL, right? So we want to solve for PAL. So PAL, which is equal to just P, which is equal to the force in the bronze, is equal to sigma, while the minus gets moved over. It's minus sigma AL times AAL, right? So this force you get is minus times a minus 11 times 10 to the third PSI, multiplied by its cross-sectional area, which they give you as 2.8 inches squared. So the force you get, P, which is equal to PB, which is equal to PAL, is equal to, let me give you that value. It's 30.8 kips. Okay. So now that we have that force, we have to use mechanics anyways, where we need this piece of information in order to solve for the mechanics part. Right? Because we're going to need, these are both deforming, right? So we're going to have to get an equation with deltas, right? So let me erase this stuff now. Let me erase this picture because we don't need this. Actually, before I erase it, I want to ask you guys something. So what would be the mechanics equation that you get from this? It's going to be with deformations, but you have to know how it adds up. So basically you have the sum of all deltas is equal to 0, right? In this case, it's not equal to 0 though, because it's equal to the total deformation, which is a gap. So in general, it's equal to 0, but you could also move the gap to this side and move it over. But in general, that's the equation, but since there's a gap, we'll always call this, you know what, sum of all deltas is equal to the gap. That's better, okay? If there's no gap, this is 0, okay? You guys you won't find this in the textbook, but this is what's happening, okay? So in every problem, this is what's happening. They should have this equation in the textbook, but they don't. Okay, let me keep that. All right, so what is this equation? I'll erase this stuff, and I'll keep the other stuff. I should keep this diagram. All I needed was that force. Okay, so the force P is equal to 30. Where was it? Afraid I lost the number. It was 30.8 kips. Okay, so what is this equation that we get? So we have delta of the aluminum, right? This is there's two types of deltas, right? After the gap closes, it's going to be in compression, right? So it's going to be shrinking. It's going to deform. It's going to get crushed, right? But it's going to expand from the thermal expansion. So you have delta aluminum for the thermal expansion, and that's positive, right? Because it's expanding. But after the gap closes, it's going to try to get compressed, right? So you have to add another term. You have minus delta AL from the mechanical. The mechanical delta is the PL over AE. Do you guys know what the thermal expansion is? It's alpha delta T times L. You guys learned this, right? I'll write the equation out after, okay? So what else do you have? So this is for the aluminum. What about for the steel?
It would be the same thing.
Yeah, same thing. So it's delta ST minus delta SM is equal to delta gap, right? And we know what the gap is. The gap is, that's why I shouldn't erase it. I was being stupid. Okay, this is 0.02 inches. This was 14 inches. It's 18 inches. I don't want to erase this. Okay. This is a gap. Okay. So this delta is equal to 0.02 inches, right? So this is what we have. We have alpha AL delta T L, right? That's a deformation of the aluminum. So that's this term over here. This term over here is equal to minus PAL times the original length over the cross-sectional area times the Young's modulus. And then this term over here is equal to plus, right? It goes plus minus plus minus. Okay, so it's alpha, this is the steel, alpha delta T L, and then you have minus P S L over A S E. This should be an S. These L's aren't the same, right? So this is AL. Okay. And this is equal to the gap. Well, the gap we know is equal to 0.02 inches. All right, so everyone sees what's going on, right? Okay, so we have this force. We just discussed before from statics, which we found. P is equal to PAL, which is equal to P bronze. Wait, I used this is bronze. Sorry about that. This is B. B. You always work with steel in this class, and you think everything's steel. Okay, so that's a mistake. I'm glad I caught myself. This is B. B, B, and everything else is good. These are all B's now. B. Okay. Any mistakes before I go on? All right. So this is the same equation though. It's just the material's different. I thought this was steel for a second. Okay. So basically, what we're looking for is delta T, right? Because if we have delta T, we could get the final temperature, right? You guys follow the thought process? Okay. So let's see what we have. We have this. We have this was given in the problem. We have this, all this. We have the force. We have everything. We don't have delta T. That's what we're looking for, right? So we have to rearrange this to solve for delta T. Well, okay, so what you could do is what? Move this and this over to the other side, have everything known, and then divide by the thermal coefficient, thermal coefficients times the original length of each material. So we want to solve for delta T. So that's equal to, so I'm moving this and this over. So you have PAL, let me just call it P because they're both P. So let me factor that out. So you have P times, let me see how I did in my notes. It's P times LB over AB. This is just algebra, so you guys can work this out. It's not complicated what I'm doing here. Plus the gap. So all I did is move this one and this one over to the other side. And then it's all divided by these two terms plus these two terms. So it's alpha AL, L AL plus alpha B LB. Okay. Right? So this is what you get, and everything here is known, right? We know the force is 30. Do you want me to like plug it in or no? I don't have to do that. So do you guys know what the original length? It's just for brass, it's just 14, right? So this is 14 inches. This is equal to 18 inches, right? The gap's equal to 0.02 inches. And this they give you, so you could just plug and chug, and they give you this, and they give you this. Okay? So the final temperature difference you get is, it's 120, it'll be on Blackboard anyways if you want to see all the numbers, degrees F, okay? So that's a final temperature change, right? So from this, what could we get? We're after the final temperature, we could get that now. We know the final temperature, because delta T is equal to what? It's the final temperature minus the initial temperature, right? That's what a change is, okay? So it's a final minus an initial. And we're looking for the final, right? We know the change in temperature, we know the initial temperature, we could get the final temperature. Okay, so TF is equal to delta T plus TI, the initial temperature. So TF is equal to 126.6 degrees F plus the initial temperature, which was 75 degrees F. Okay, so the final temperature you get, it's 201.6 degrees F. Alright, so you got the final temperature, and now what they want to know in the second part, they want to know the deformation. Oh no, they want to know the length of the aluminum after it expands and then shrinks a little. Okay, so they want to know the total. Okay, the exact length of the aluminum bar at the end. Okay, so how are we going to find that? How are we going to find the exact length of the aluminum bar? Does anyone know? So for part B, they want to know the exact length of the aluminum bar. How will you find it? So after everything just happened, we had the equation up there before, but I erased it. So you want to find the deformation of the aluminum rod and then add it to its original length. You guys follow? Okay. So what is that? So delta AL is equal to, it's going to expand first. So the thermal expansion, remember, is delta AL, delta T. We found delta T already, and AAL, right? That's positive, but then we have the mechanical delta. After the gap is closed, it's going to be smushed. So it's minus PAL L over AAL E AL. Okay. So this is the change in length of the rod. So delta AL is equal to, I erased all that stuff. Let me just plug and chug the numbers. It's 18 inches multiplied by, this is the length, okay? This is 18 is the length. The thermal coefficient of expansion is 12.9 times 10 to the negative 6, 1 over a degree F, times it, the change in temperature is 126.6 degrees F, which we found before. And then I'm going to bring down here so I can get it. And then you have minus 30 times 30 kips. So it's times 10 to the third pounds times 18 inches all over 10.6 times 10 to the 6 psi times 2.8 inches squared. Okay. All right, this was a force P, which we discussed before. This is PL over AE. Well, I actually have E over here and A over here, but that doesn't matter. Okay? So this is what you get. And now for the total deformation of this thing, it comes out to 0.01072 inches, right? But they want the exact length. Okay? So this is a change in length. This is the change in length, so how do we find the exact length? Delta is the same thing as this. Delta AL is the original length. I don't know, what do you want to call it? The original length. Okay, so they want the exact length. So it's the same thing like the temperature difference. So it's final minus initial, right? So this is delta, this is a change in deformation. So it's original length minus the final length minus the original length. So we want the final length. So how do we get that? So it's just a change in length plus the original length. So LF is equal to the initial length plus the deformation, right? So it's just 18 plus this number, so it's 18.01072 inches. Right? Any questions? It's too hot in this room. Let me do one more problem because this is important.